a revision lesson on movement or motion. This is going to be one of two, and this one's going to deal with the basics of speed time graphs, velocity time graphs, etc., etc. Okay, first of all, we need to understand this term average velocity, average speed, or velocity. And that talks about if we're imagining an object moves a certain distance in a certain time. However, what you might find is that an object might start off, I mean, if you imagine Usain Bolt in the 100 meters, he's starting off quite slowly and then he picks up speed and keeps continuing to build up speed. However, when we talk about his average speed, what we're talking about is the distance he covers, and that's the total distance he's covering, divided by the total time that he is covering. So in actual fact, with Bolt, it's approximately covering, well, he's definitely covering the 100 meters in approximately, let's say, 10 seconds, just to make life easier. And that gives us 10 meters per second. However, we know that he doesn't start instantly at 10 meters per second. He starts much slower, and he actually finishes faster than 10 meters per second. But this is the average speed that he covers. Okay then, so remember that total distance and total time. So therefore, it's important here to talk about, I just said at the beginning there, the difference between speed and velocity. And these two concepts are very, very similar and can be confused often, but a knowledge of what separates them is really important. Speed is often just a value. There's just a value to the number, like 5 meters per second, 10 meters per second, 20 meters per second, etc., etc., 20 miles per hour even. Whereas a velocity, of course, it's the same in terms of it has a value, but it also has a direction. So you'd have to say it's going 20 meters per second in a certain direction, one way or the other way, east or west. It has to have a direction to it. And that becomes very important when we start graphing the function, graphing velocity or speed, because it very much matters which way the line goes as to which direction is being moved in. In a similar way as well, our distance, which is merely just a value, has another quantity known as displacement. And that quantity, it has a value and a direction. So it matters if you're going forwards or backwards or left or right. We call the ones which have just values, we call them scalars. Whereas those that have values and directions, we call vectors. And I'll show you the use of them in just a minute. So here goes with our first use of a graph. First of all, you need to be able to interpret distance or displacement time graphs. The time is they always have time axes. And what I'm going to draw in here is a displacement graph. And that's often drawn in meters. We will have a line is often, of course it's a line. Let me give you some values so I can describe what's happening here. Here we go, in a certain time period as well. Cross for a while, for 5 seconds. We're going to come back down here for, sorry, that should be 15 seconds, 20 seconds, and finally 25 seconds. Okay, so a displacement time graph. So first of all, let's talk about what's happening with this object that's moving. Well, first of all, it has moved away from its point, its starting point, and it's moved away by 150 meters, and it's taken 10 seconds to do that. Then this flat part along here means that it actually stayed still. It was at rest. So this part is at rest. And then the line comes back down again, which implies, because this is a displacement time graph, it means that actually it moved back towards where it started from. It took 10 seconds to move away from the point. It rested for 5 seconds, and it takes 10 seconds to get back to the point. Okay, so what can you interpret other than just describing this graph? Well, the gradient of the graph is equal to the velocity. And that's very important. You'll have to be able to work out the gradient of a displacement time graph. What do I mean by gradient? Well, the gradient, I think we learn in maths, is the rise divided by the run. In other words, how much has covered on the y-axis in terms of the units you're given. So the rise divided by the run, that which is on the x-axis, in the units given. So in this instance, the velocity is going to be our rise over our run. I'm going to take the rise from this point here to that point there, which is, in terms of these units, 150 meters, and the run will be 10 seconds. And so in this instance I have 15 meters per second is the velocity in the first point. Of course this is at rest, zero velocity. What's the velocity from this point here to this point here? Well, the velocity, of course, is going to be the same again. However, this time we've actually got a negative 4, so I'm going to put minus 150 over the 10 seconds. It's actually the rise, which gives you minus 15 meters per second. In other words, what this is saying is the velocity, the minus implies it's going backwards. It matters which direction you're moving in. Really important point there. Okay, here is another instance, a drawing of a displacement time graph. In meters. This time, I wonder whether you know what that implies. I'm just going to sketch it. Well, that implies that something is changing speed. And if it's changing speed, we call that accelerating. Very important point. And that is what we're going to move on to now. Right, I thought I'd best describe this. What does accelerating mean? Accelerating means a change in speed. So accelerating, we've said that, change in speed. Let me give you an example on Earth. We know that objects fall to Earth and they change in speed as they fall to Earth. The acceleration of Earth is the same as g, which we have as 10 meters per second squared. What's that saying? Well, it's saying that you have a change in speed of 10 meters per second every second. So bearing that in mind, if I come back to my example here, what happens after 1 second with an object falling? What happens after 2 seconds? What happens after 3 seconds? Well, if it's travelling initially at 0 meters per second, it is stationary, then after 1 second it picks up 10 meters per second in speed. After 2 seconds, it's going to, in the 1 second gap, it's picked up an extra 10 meters per second, or in 2, it's going at 20. In 3, it's going at 30 meters per second, and so on. Okay, let's reverse that situation. Let's say I throw the ball upright. I've got a dropping ball. Of course, you know g acts downward. Let's imagine I throw it up with 40 meters per second. I let it go with 40 meters per second. Then what does the gravity do? Well, after 1 second, it slows it up by 10 meters per second because this is a vector. It matters which direction it's pointing in. What do you think happens after 2 seconds? Well, it's travelling at 20 meters per second. I'll just draw it a little bit to the side because I haven't got much space here. 3 seconds, 10 meters per second. 4 seconds, it's travelling at 0. What happens then? It turns round, or it starts to fall. And at 5 seconds, it's travelling, interestingly, at 10 meters per second. 6 seconds at 20 meters per second. and we carry on 7 seconds, 30 meters per second, and at 8 seconds, 40 meters per second. Of course, with the whole of this situation, I'm ignoring air resistance. So therefore, what are we saying with acceleration? Well, acceleration is equal to the change in speed divided by the time taken. Change in speed is in meters per second, time taken is in seconds, so therefore we write this as meters per second squared. If you want the triangle, we have this. Because the equation symbolically is written as such: acceleration is change in velocity divided by change in time. So let me just look back up to here. If we start at this one here and we move to that one there, the change in speed here is 10 meters per second. The change in time is 1 second. So therefore what's happening? Well, g, the acceleration, is 10 meters per second each second. What happens if I move from this point here to this point here? Well, my change in velocity there is 20 meters per second. My change in time, of course, has been 2 seconds. So once again, my acceleration is change in velocity, which is the difference, 20. Change in time is 2, giving me once again 10 meters per second squared. So can you see the importance of that change in velocity? Okie dokie, so let me give you some examples to work on then. Some 3 examples. Let's imagine I have an object that moves from 5 meters per second and it goes to 25 meters per second, and the time taken is 4 seconds. What's the acceleration? If you think you know, hit pause, give it a go, otherwise here comes the solution. Acceleration is change in velocity over change in time, which gives me the difference. The change in velocity is 25, but it started at 5, and it's got 4 seconds to do it in. So therefore I'm working at 25 meters per second squared. Excellent, hope you got that right. Here's another example. What would happen if I moved from, well, slightly different. I have an acceleration of 0.3 meters per second squared. That occurs for 60 seconds, and I start at 5 meters per second. What's my final velocity? If you think you know, hit pause, otherwise here comes the answer. Okay, now we can write the change of velocity is the final velocity minus the starting velocity, or u, initial velocity. So then what I'm going to write is I'm going to write here, bearing in mind my triangle, I'm looking for the velocity, acceleration times time. So the change in velocity is the acceleration times time. And what I'm looking for is the final velocity. So that's acceleration times time plus the initial velocity. I have 0.3 times 60, and add that to my 5 meters per second starting time, which gives me, this gives me 18 plus the 5, 23 meters per second. I hope that made sense. And finally, just a very quick example. Let's try another one. I'll just squeeze it in here. What happens if we've got a car that's moving at 18 meters per second and then goes to rest in 3 seconds? What's the acceleration this time? If you think you know, hit pause, otherwise here comes the answer. Well, the acceleration is the change in velocity over the change in time. My change in velocity is actually minus 18 meters per second because I've gone from 18 to 0, and it happens in 3 seconds. So therefore, I have, and my mind's gone blank, 6 meters per second squared minus, which means it's a de-acceleration. It's vector again. It matters which way it's going. Okay, I suppose the last point we come to is that how would you graph that function? How would you show acceleration on a graph? And this is shown on a velocity, meters per second, time graph. Here's an example. Let's describe what's happening here. This thing has travelled, the line has gone up and then it's gone flat. The time it's taken is 3 seconds and then 4 seconds. Not the best axes, but nonetheless. Let's describe what's happening first of all. This straight line, first of all, you notice it's a velocity time graph. So this straight line here implies that it's picking up speed or accelerating. This flat line here means a constant speed. So whereas it was different from the first instance, let me pick up the first instance again, because the first instance talked about a constant speed and then rest, because it's a displacement time graph. This one is now an acceleration and a constant speed because it's a velocity time graph. The acceleration actually equals the gradient of the line, and the distance travelled is the area under the graph. Please remember those two concepts. Let's work those out very quickly. So the acceleration is going to be the raise over the run, 15 over 3, giving us 5 meters per second squared. The distance, well, it depends. Let's say the distance in the 3 seconds. That's the area, which is the same as a half times the base times the height, because in effect we're looking at the area of this triangle. That would give me a half times the base of 3 times the height of 15, which is 45, half of 45, 22.5 meters. Of course, if we were looking for the distance over 4 seconds, then I'd have to add to that the area of that square. Let me give you an example to work through. Here we go. I've got a velocity time graph. Note my use of units and all of these to be accurate. Moving at 20 meters per second. That happens for 10 seconds, and then after 15 seconds it comes to rest. That's probably a sharper line than it ought to be, but that's the data. Those are the data, should I say. Okay then, what I want to know is, what's the deacceleration here, because obviously this is going from a speed to 0. What's the deacceleration, and what's the distance covered in the 15 seconds? Okay, if you think you know, hit pause, otherwise here comes the solution. Right, the acceleration is the gradient of this line. The raise is 20 over the run of 5 seconds, so therefore we've got 20 over 5 seconds. But of course this is a deacceleration. It's gone from a high value to a low value. That gives me minus 4 meters per second squared. And what about the distance? Well, that's the area, But it's actually area of two parts. It's this big block here, which is straightforward. That's 20 times 10. But also we have the area of this triangle here, which is a half times the base of 5 times the height of 10, which gives us 200 plus 25, 225 meters it has travelled whilst deaccelerating. Okay, I hope that all makes sense. That's part one. Part two will be uploaded shortly.